Hey, welcome back, everyone. Thank you for joining us. I'm Steve.
And I'm Scott.
Together, we're Backyard Musing, broadcasting Apple Valley, People's Republic of Cali Atlan.
And we are talking quantum science tonight.
Again, there's just
Or
so many
today,
facets
this
to this,
afternoon.
man.
Yep.
It's crazy. Scientists have linked nuclear spins inside silicon chips, marking a leap towards scalable quantum computers. Engineers at UNSW, I don't know what that stands for, have achieved a major breakthrough in quantum computing by creating what are known as quantum entangled states. And this, we know about entanglement for quantum physics. In this phenomena, two particles become so strongly connected that their behavior can no longer be described independently of each other. The team accomplished this using the spins of two atomic nuclei, a resource considered essential for quantum computers to outperform traditional machines. Would you like to know more?
UNSW, Sydney, one of the best universities in Australia.
Oh, Sydney.
Yep. All right. The findings published in Science on September 18th, 2025, mark a crucial step towards the development of large-scale quantum computers, which are widely seen as one of the most ambitious scientific and technological frontiers of the 21st century. According to lead author Dr. Holly Stempf, the work demonstrates a path to building future quantum microchips with technology already available. Okay.
Quote, we succeeded in making the cleanest, most isolated quantum objects talk to each other at the scale at which standard silicon electric devices are currently fabricated, she says. A central difficulty in designing quantum computers has been finding the right balance between two conflicting requirements, protecting the delicate quantum states from interference and noise, while still allowing them to interact in order to perform computations. This challenge explains why different types of quantum hardware remain in competition. Some systems can perform operations very quickly but are highly vulnerable to noise, while others are better protected from interference but much harder to control and expand.
So would that mean that there's probably not a whole lot of collaboration here then? They're probably all keeping this stuff.
Yeah, it's probably like the Apple and the IBM. Maybe it's there's so many different things. Remember we talked about that. It was a university where two branches of the university had set up a fiber optic and they were communicating.
Back and
quantum.
forth.
Yeah, quantum.
Yeah. The UNSW team has invested in a platform that, until today, would be placed in the second camp. They have used the nuclear spin of phosphorus atoms implanted in a silicon chip to encode quantum information. Quote, the spin of an atomic nucleus is the cleanest, most isolated quantum object one can find in the solid state, says Scientia Professor Andrea Morello, UNSW School of Electrical Engineering and Telecommunications. So, is that a science professor, you think? Scientia?
Yeah.
Okay.
Electrical engineering and telecommunications. Yeah.
All right.
Over the last 15 years, our group has pioneered, this is a quote, all the breakthroughs that made this technology a real contender. 15 years in the quantum computing race. We already demonstrated that we could hold quantum information for over 30 seconds, an eternity in the quantum world, and perform quantum logic operations with less than 1% errors. Remember, that's the thing, the percentage of errors, and only less than 1%. That's really good.
Yeah. Quote again, we were the first in the world to achieve this in a silicon device, but it all came at a price. The same isolation that makes atomic nuclei so clean makes it hard to connect them together in a large-scale quantum processor.
Until now, the only way to operate multiple atomic nuclei was for them to be placed very closely together inside a solid and to be surrounded by one and the same electron.
Quote, most people think of an electron as the tiniest subatomic particle, but quantum physics tells us that it has the ability to spread out in space so that it can interact with multiple atomic nuclei, says Dr. Holly Stempf, who conducted this research at UNSW and is now a postdoctoral research researcher at MIT in Boston.
This reminds me of Ant-Man. You know, how Ant-Man could change to microscopic level and then huge level. Remember that?
I don't know. I wouldn't know Ant-Man if you walked in my house right now.
Well,
Sorry.
it's a Marvel series.
Yeah.
Okay. Quote, even so, the range over which the electron can spread is quite limited. Moreover, adding more nuclei to the same electron makes it very challenging to control each nucleus individually.
Quote, by way of metaphor, one could say that until now, nuclei were like people placed in a soundproof room. Dr. Stemp says they can talk to each other as long as they are all in the same room, but the conversations are really clear. But they can't hear anything from the outside. And I need one of those rooms. And there's only so many people who can fit inside the room. I love that too. This mode of conversation doesn't scale. I don't quite understand that. So,
quote, with this breakthrough, it's as if we gave people telephones to communicate to other rooms. All the rooms are still nice and quiet on the inside, but now we can have conversations between many more people, even if they are far away. That's awesome.
Yeah. The telephones are, in fact, electrons. Mark van Blankenstein, another author on the paper, explains what's really going on at the subatomic level. Quote, by their ability to spread out in space, two electrons can touch each other at quite some distance. And if each electron is directly coupled to an atomic nucleus, the nuclei can communicate through that. Okay.
So how far apart were the nuclei involved in experiments, you ask? The distance between our nuclei was about 20 nanometers. That's a quote. 1,000th of the width of a human hair, says Dr. Stemp.
No way. How can you measure that?
Continue the quote. That doesn't sound like much, but consider this. If we scaled each nucleus to the size of a person, the distance between the nuclei would be about the same as that between Sydney and Boston.
Wow. Well, that's a distance.
Yeah.
He adds that 20 nanometers is the scale at which modern silicon computer chips are routinely manufactured to work in personal computers and mobile phones. Quote, you have billions of silicon transistors in your pocket or in your bag right now, each one about 20 nanometers in size. This is our real technological breakthrough, getting our cleanest and most isolated quantum objects talking to each other at the same scale as existing electronic devices. This means we can adapt the manufacturing processes developed by the trillion-dollar semiconductor industry to the construction of quantum computers based on the spins of atomic nuclei, unquote.
Despite the exotic nature of the experiments, the researchers say these devices remain fundamentally compatible with the way all current computer chips are built. The phosphorus atoms were introduced in the chip by the team of Professor David Jameson at the University of Melbourne, using an ultra-pure silicon slab supplied by Professor Kohei Ito at Keio University in Japan.
Okay. By removing the need for the atomic nuclei to be attached to the same electron, the UNSW team has swept aside the biggest roadblock to the scale-up of silicon quantum computers based on atomic nuclei.
Okay.
So we're pushing forward in the world of quantum
advances. Yep. And you heard it here.
Yep. But we didn't write this.
We're not experts.
Yep. Definitely not for me anyway.
Okay, folks. Thanks for joining us.
Take care. We'll see you tomorrow. Have a good night.